So for the integrated design project for reaction engineering, first we have first to produce hydrogen gas, water and natural gas must be mixed in a mixer and undergo steam methane reformation with a chemical equation of CH4 in the gas phase and reacts with H2O in the gas phase. Okay, to produce carbon monoxide in the gas phase and 3 moles of hydrogen gas in the gas phase. And the carbon monoxide will then further undergo water gas shift reaction. Okay, and this water gas shift reaction is as follows: carbon monoxide in the gas phase reacts with water in the gas phase to produce CO2 and H2 in the gas phase. Now, the main purpose of this water gas shift is because when the carbon monoxide, carbon monoxide is a very harmful gas, so it cannot be emitted directly to the environment. So we have this water gas shift mainly to convert the carbon monoxide to carbon dioxide. And additionally, it will produce additional hydrogen gas, which is a plus point. Okay. For the next one, the catalyst used, we have several researchers, and as you can see, ruthenium has a higher activity coefficient than nickel. Okay. However, okay. However, nickel is recommended because although ruthenium has a better relative activity than nickel under operating conditions of 550 to 700 degrees Celsius, which is our operating conditions of the steam methane forming reaction. However, ruthenium is a very highly toxic metal and regarded as carcinogenic substances. It is also considered a very expensive transitional metal, and nickel is cheap and easy to get. Furthermore, it can also withstand higher temperatures in comparison to ruthenium. Okay, for a description of the system for the steam methane reformation reaction, it occurs under high temperature, which is at 550 to 700 degrees Celsius. Okay, and in this reaction, the methane reacts with steam at a pressure of 1 bar and 1 atmospheric pressure in the presence of a catalyst, which is in this case nickel. And the result of it is to produce hydrogen, carbon, and carbon monoxide. Okay, steam reforming is an endothermic reaction whereby heat must be supplied to the process for the process to proceed. Okay. Subsequently, water gas shift reaction can be divided into high temperature water gas shift and low temperature water gas shift here and here. The high temperature water gas shift is performed at 350 degrees Celsius to 450 degrees Celsius with iron oxide based catalyst. And the low temperature shift, water gas shift, is performed at 190 degrees Celsius to 250 degrees Celsius with copper zinc oxide based catalyst. Okay, in a final process step called the pressure swing adsorption, carbon dioxide and other impurities are removed from the gas and leaving the essential pure hydrogen. Steam reforming can also be used to produce other forms of fuels such as ethanol, propane, as well as gasoline.
Table 1 shows the stoichiometric table for SMR reaction. Inside the table, we have the species, symbol, initial flow rate, change of the flow rate, and the remaining flow rate, and last but not least is the concentration of the component. For this reaction, the limiting reactant will be methane and the excess will be the steam. As per request, we are required to produce 30,000 tons per year of hydrogen gas. After converting it, we get 1,695.38 kmol per hour. Thus, this is also equal to the FD inside the stoichiometric table. Figure above, we can determine the molar composition of methane in natural gas, where around 94% of natural gas is methane. With carbon steam ratio equal to 3, Therefore, we can calculate the molar composition of the outer stream of the mixer through air-cone simulation. The molar composition is found to be methane equal to 0.2345, water equal to 0.75, and inert equal to 0.0155. For SMR reaction, we calculate that the conversion is equal to 0.893, delta is equal to 2, expansion factor equal to 0.469.
From table 2 is the stoichiometry table for water-gas shift reaction. Before we start the calculation, there are two assumptions to ease the calculation process. First, we must assume that the product of SMR reaction is the feed for the water-gas shift reaction. Second, water-gas shift reaction have the same conversion as SMR reaction. Carbon monoxide is the limiting reactant while steam is supplied in excess. So, the data value of each component is shown in the table below. For the water-gas shift reaction, we assume that the conversion is 0.893 and the delta is equal to 0. Because of the delta is equal to 0, thus the expansion factor is also 0. The molar flow rate and concentration of each component is shown in the table below. According to Abbas, Dupont, and Mahmoud, we found out that the weight of the required catalyst for this reaction is 5,797.8 kg, and the total volume of the reactor is 61.92 meter cube. However, for water-gas shift reactor, the weight of the catalyst required is 8.563 kg, while the total volume of the reactor is calculated to be 0.033 meter cube. In slide 12, to maximize the production of hydrogen gas, we have to increase the selectivity and yield of hydrogen gas. To increase the selectivity, we need to decrease the concentration of A in the second reaction or decrease the rate of reaction in the second reaction. In order to decrease the concentration of A, we need to use low pressure since the stream in gas phase temperature of 700 degrees C. Another way to increase the selectivity is to use a packed-bed reactor with recycled streams. According to Lee, certain membranes that have perfect selectivity to hydrogen, such as dense PD-based membranes, are used to obtain a very high purity percentage of hydrogen, which doesn't require the need of additional purification methods such as the ones in the conventional process. Next, to increase the yield, we also need to decrease the concentration of A or decrease the rate of reaction for the second reaction. To satisfy both the conditions, we can use PBR reactor with recycled streams. According to research by Abashar, countercurrent fluidized bed membrane reactant produce a better overall equilibrium conversion.
So, talking about a type of adsorbent, comparing the adsorption capacity of both activated carbon and zeolite 5A, both adsorbents show great capability to separate hydrogen gas from the mixture. Hence, dynamic multi-component adsorption model was developed in a fixed bed of industrial scale containing two layers of adsorbent, which are zeolite 5A and activated carbon. Moving on to the next slide. To predict the best isotherm equation or model, which gives the best linear line, will be chosen as the adsorption isotherm in the hydrogen enrichment process. However, since the operating pressure in hydrogen enrichment unit is exceeding atmospheric pressure, so linear isotherm or Henry's adsorption isotherm are not valid in the process. Hence, the hybrid Langmuir-Friendlich equation will be extended to a n-component mixture, also known as loading ratio correlation (LRC), and this equation would be the isotherm used to fit the data in hydrogen enrichment unit. Generally, all of its parameters can be considered to a function of temperature. So table 3 shows the LRC coefficients for activated carbon and zeolite 5A. So the absorption data of all components of zeolite 5A adsorbent in figure 5, while on activated carbon in figure 6, are fitted using the LRC model. It is observed that the extent of adsorption for carbon monoxide and carbon dioxide increase quite rapidly from minimum to middle pressure. Consequently, because of exponent n in the LRC relationship, this model could fit the experimental data more accurately. So in the hydrogen purification unit, we decided to use a two-layered pad bed column. The model for the adsorption bed consisting of a 5.38 meter activated carbon layer at the top of the bed and a 1.87 meter zeolite 5A layer at the bottom loaded in a column of 3.616 meter diameter.
Figure 9 shows mass transfer zone or MTZ of CO2 at temperature equal to 298 Kelvin and pressure at 20 bar. The mass transfer zone moves along the bed length in the same direction with the gas motion and gets to the end of the bed where the concentration of substance changes within the particular zone. Approximately, the concentration starts to change at bed length equal to 2 meter at time 200 seconds until the bed length equal to 4.25 meter at time 400 seconds and then repeated. Thus, the calculated MTZ equal to 2.25 meter. From the above equation, the used bed length up to the breakpoint, which is HB, can be determined, which is 5 meter. Figure 10 shows the breakthrough curve of all components in this system. It can be seen that the mole fraction at time 600 seconds increased drastically since the unadsorbed solute leaving out the adsorption bed column. Therefore, breakpoint, which is TB of the system, is 600 seconds. Now, scale-up design can be performed. The scale-up principle is the amount of unused bed length does not change with the total bed length. In case the required bed length is 700 seconds, thus the new total height can be calculated, which is 8.083 meter. To achieve 99.9% of hydrogen gas production, pressure swing adsorption or PSA is the first strategy to be implemented. This system carried out using activated carbon and 5-azolite as adsorbents, which have a good performance. PSA operates on the principle that some gaseous components adsorb preferentially to others on highly porous materials. These materials adsorb larger amount of impurities at high partial pressure than at low partial pressure. Thus, the column is fed with high pressure feed gas. The second strategy is the pressure swing adsorption, which is PSA systems are designed with either 4, 5 or 6 adsorber vessels and different modes of operation. This will ensure a high production of H2 with high purity since the feed is keep flowing. There is time for the first adsorber column to regenerate. The feed will go to the second column while the first adsorption column regenerating. Therefore, the adsorbents used in this process are always in a continuous process. Adsorbents can be regenerated by shifting the equilibrium distribution. There are several ways to do it, such as increase in temperature, reduction of the pressure, purging with an inert fluid, reduction in concentration, displacement with a more strongly adsorbing species, and change of chemical condition, such as pH. However, in this study, the suitable way to regenerate it is by reducing the pressure, since the system is in gas phase. This process, also known as pressure swing adsorption, which is PSA. Pressure swing adsorption is a technology used to separate some gases species from a mixture of gases under pressure according to the species molecular characteristic and affinity for an adsorbent material.
To make our work and research easier, we separated the tasks so that everyone will only focus on one aspect of the project. We then share all the parts to each other so that we are all aware of the work that our partner did and can follow up with the same writing style and similar reference so that we are not mixed up with everything. We managed to finish all the incubator project and also video presentation in time. We all contributed to the task for the completion of both the report and video presentation. Throughout the research work, the bond between us did not only stay as good mates, but became closer and become friends. Last but not least, we were also able to relate and apply all the knowledge that we have learned from separation process 2 and reaction engineering 1 into this integrated project. Thank you.